So in preliminary, we looked at discrete distributions. Now we want to look at continuous ones and how is it different. But before we do that, let's just recap what probability distributions and so on are. Remember, we're looking at random variables, which is merely a quantity, and the value of that quantity is basically its probabilities. It depends on chance. And then we have the probability distribution, is where we then go and list all the possible values of that random variable. Now, simple little example. Eggs in a supermarket sold in boxes of 6. Number X of broken eggs, so X is going to be our random variable, has a probability distribution given by so. We never get a box with all eggs broken or 5 eggs broken. There you go. Is that realistic? Yeah, I suppose. That is our probability distribution. And properties then of it, we know. We know that we have to end up with a positive number. You don't have negative probabilities, but further than that, we know they all have to add up to be 1, sum of all the probabilities. And if the probability is the same for every single outcome, then we just have a uniform distribution. So X, as I say, is going to be our random variable. In this case, it's a discrete random variable. And the expected value we found was this expression here, the sum of, we get that random variable and multiply it by the probability of X, probability of the outcome. So notes there. Expected value and average or mean have the same value. They're not the same thing, they just have the same value. And because it is the same value, we still think of it as a measure of central tendency, where, an estimate of where the middle of the data is. Now, if you went and bought 10 of those boxes, how many eggs would you expect to be broken? There's our table. We'll add in an extra row now, where we'll work out the XPX and sum that up. And our expected value is the sum of that row. So the probability of 0.3. Well, therefore, if there's 10 eggs in the box, I've got a probability of 0.3. I'd expect 0.3 of the box to be broken. So 3 broken eggs is what I would expect. Then we looked at variance, and there were different ways of doing it, but this was probably the simplest way, or another way of thinking about it: expected value of x squared minus the expected value of x squared. Expected value of x squared, it's still expected value, but now because it's the expected value of x squared, we say x squared times the probability of x. Okay, and that's a measure of spread, how spread out the data is. Now, standard deviation we tend to use more than variance. The reason for that is to do with the units. So we want to get it back to the same units as the data, whereas variance is units squared. So we find the square root, basically. Standard deviation, we find the square root of the variance. Well, what is our standard deviation for our eggs? Now I'll add in another row for x squared times the probability of x. Work out those. So expected value of x squared, add up that row, we get 0.6 minus the expected value of x, 0.3 squared. 0.51, square root of that, 0.714. So relative frequencies then. When we sample our data, we talk about relative frequencies, not probability. Probability is when we have the entire population, when we have every piece of data. Whereas relative frequency is just when we have a sample of the data. And it's an estimate then of that theoretical probability of the population. Now what happens is, as that sample we draw on increases, then the theoretical probability and the relative frequency are getting closer to being the same result. Here's this one. Students in Year 12 surveyed to find out how many siblings the students have, and we put it into our frequency distribution table. But notice this, it's now a frequency distribution table. So I haven't got the probabilities here, I have the frequencies. Because if you're collecting data, you would be counting how many pieces of data you got. You wouldn't be saying, oh, I just got this result. What's the probability of that? Oh, I got this result. You'd be just recording the frequency. The next row is equivalent to the probability row that we had before, but we now call it relative frequency. So a different notation, F with an R on it. And then the third row I've put in there is a cumulative frequency. So we're just adding up those relative frequencies as we go along. Okay. They want us to create the relative frequency histogram and the polygon as well. Well, there's the histogram. The polygon is when we join it up to the middle of the top. But we tend to also go one before and one after. And they're on the axis because, of course, they have a frequency of 0. And we get that. And there is a very good reason for doing that, and we'll see that. If we calculate the total area of the rectangles we've got there, I'd end up with 1. Now, no surprises there, because really all I've done is I've added up all the probabilities. Because the width of my rectangle is 1, I'll end up with 1. If the width of my rectangles was 2, I would have ended up with 2, twice the sum of all the probabilities. If the width was a half, I'd end up with a half of the sum of all the probabilities. But what about the area under the frequency polygon? And nicely, because they're straight lines, we can use the trapezoidal rule to find that value. And it also turns out to be 1. And that is why you join your histogram up, so you can get those areas to be the same. Now, it probably was never explained way back in, I don't know, when's the first time you do those sort of things? They just told you, oh look, extend the graph out to here and here, but that's why. Because there is actually this relationship between the area under, well, both the polygon and the histogram, and the probability as well. We're now going to draw a cumulative relative frequency histogram. Well, that's a mouthful. Cumulative relative frequency histogram, and ogive, fancy word for polygon, for this data. There's the histogram. Remember, when you're drawing an ogive, we actually draw the line on the diagonals and then join up to the vertex, and so on as we go up. Calculate the 5-number summary and the interquartile range. Well, there's the picture again. 5-number summary, those 5 key pieces of information. Now, the minimum is, of course, 0. That's nice and easy to work out. Q1 is 25%. I can just go up my scale, probability of 0.25. That's what I'm looking for here. And read across, bang, oh, it's 1. Q2, or the median, would be at 0.5. That also is 1. And Q3, that one ends up in 2, and maximum is 6. There's our 5-number summary. If we wanted to draw a box and whisker plot, we could, but they're more interested in interquartile range, and that's when we get Q3, subtract Q1, so interquartile range is just 1. So that'll do us today. We'll just leave it with that. So 16A, just reminding ourselves about all those key things before we jump into continuous data.